You might have heard the term ray tracing. Today we will be talking about its big brother, raymarching. Raymarching is a very popular and a powerful rendering technique often used to create 3D shaders. Hello everyone and welcome back to the channel. My name is Digvijay Gohil and today we will create a simple raymarch shader to render a 3D sphere in a box mesh. For the tutorial I will be using Godot 4.2 and this video will be the basic introduction about raymarching. So if it sounds interesting to you, stick around and we will dive into the topic right after the intro. So the first thing is, what is raymarching? Imagine that we have a camera and it has a position in 3D space. We will call it ray origin. Then we will have a direction in which our camera is looking at. We will call it ray direction. In our scene, if that ray intersects with any surface, we will get that point and color that pixel. Obviously, we will do that for every pixel at which our camera is looking at. Now we cannot magically get the intersection point. So in order to get that intersection point, we will first ask a simple question that what is the closest distance from our ray origin to the surface. Then we will get a point which is the closest one to our ray origin. We will count the distance to that point from our ray origin. Then we will move forward that much distance in our ray direction. Now we will get this point. Again we will ask the question that what is the closest point from the new point to our surface. Then once more we will march that much distance in our ray direction. We will continue the process until the distance becomes so small that we count that as a hit. This is the raymarching in a nutshell. And it is called raymarching because we are literally marching along the ray. Sometimes it is also called sphere tracing. Alright, simple enough. But now the question is, how do we get the closest distance to our surface? Well, to calculate that, we will create something called SDFs, which means signed distance functions. Now SDFs can be different for different surfaces. Here we want to calculate the closest point to our sphere. For that, we will calculate the distance from our ray origin to the sphere position. Then we will simply subtract the radius of our sphere to get the closest point. Then we will get a new point along our ray direction. Then from the new point, rinse and repeat until we hit something. Okay, that is all the theory for this video. Let's jump into Godot. Here let's first create a cube, so add node, mesh instance 3D, then select box mesh. Okay, we have our cube. Now let's create a shader for our cube. I will call it raymarching. Let's also create a material for our cube. Assign our shader to our material and apply our material to our cube. In our shader, first I will set the render mode to unshaded. I don't want it to interact with lights, and let me clean this up a bit. In our fragment processor, let's make our cube black. So let's create a vector 3 color. And assign it to our albedo. Now to write the raymarcher, we need ray origin and ray direction. So vec3 ray origin equals, and let me hard code it that I want my camera at 0, 0 and -2. And for ray direction, we want to march forward for every pixel, so let's use our uv.x, uv.y and 1, and we want to normalize that. Hang on, let's just first visualize our UV. So color.rg equals UV, and you can see that our UVs are kind of messed up. That is because in Godot, the default box mesh is UV unwrapped to show different texture for every faces. So to fix our UV issue, we need to multiply our UV with vec2 of 3 and 2. How I came up with these numbers? Well, it's in the docs. Then we take the fraction part of the entire thing, and I want the origin of our UV in the center of each face, so I will subtract 0.5. Let's visualize our calculated UV, and boom, we have nice accurate UVs. Now in the ray direction, let's also use our calculated UVs, and let me just visualize our ray direction to see if we calculated that correctly. So and yep, we did it correctly. Alright, now that we have our ray origin and ray direction, let's write our ray marcher, which will return a distance to the surface, and it will take ray origin and ray direction as input parameters. Here we first create a float variable to keep the track of distance we have marched from the origin. Let's call it distance from origin, which will initially be 0. Now we need one more variable which holds the distance to the surface. Then we will set up our ray marching loop for int I equals 0, I less than some maximum number of steps, because we don't want to march infinitely. We have to set a limit, and I++. Let's first define the max step. So hash define max steps 15. Then here we want to calculate a point on our ray direction, so vec3 point equals ray origin plus ray direction into distance from origin. This will be the purple point along our ray direction that I showed you earlier. Then from this point we will ask the question, what is the closest point to our sphere? So distance to surface equals get distance to surface from our point, and let me just define get distance to surface first, which will return the closest distance from our point P. So float I will just define some distance d equals 0 and return it for now. We will get back here in a minute. Alright, in our ray marching loop, now that we have the closest distance, we will add that to our distance from origin. Meaning we have marched forward on our ray. Now let's say that we have marched far enough from our origin without hitting anything. Then we need to acknowledge that okay, we have marched far enough without hitting anything and there is no point in marching forward. So if distance from origin is greater than some max distance, or our closest point is smaller than some threshold, meaning it is so close to the surface that we count that as a hit. So or distance to surface less than some surface distance. Then we want to break out from the loop. And let me just define max dist and surface dist. Also, you should tweak these fields to optimize our shader. Okay, now outside our raymarching loop, let's return our closest distance. So return distance to surface. Now back to our get distance to surface function. We want to get the closest point of a sphere from this point P. So it will be just the length of our point minus the radius of the sphere. So let me define the radius. Let's say 0.3, and actually I can directly return this. Alright, now in our fragment processor, let's get the distance to surface. So float dist equals raymarch, ray origin, and ray direction. Then we will check if our distance is smaller than surface distance, means we hit something. Then let's just turn our pixel fully red, so color.r equals 1. Else means we haven't hit anything. If that's the case, we don't want to draw the pixel, so just discard. And we have a circle on all 6 faces of our cube. And you might say that, well, that's a fancy and convoluted way to get the circle on the middle of each face. But trust me, this is a fully 3D sphere. Only reason it's looking like this is because we have hard-coded our ray origin and ray direction. We actually want to feed the position and direction of our camera, or the position from which we are currently looking at our cube from the viewport. Luckily, we can get the camera position with camera position world. It returns the camera position in world space, and the ray direction will be the vertex position minus camera position. Now it looks like we have messed something up, but if we move the cube to the origin of our world, and if we look around, then we can sometimes see our sphere. And the reason is that our camera position is in world space, but our vertex position is in view space. Both of them need to be in the same coordinate space. So let's just convert the vertex position in world space. We will get inverse view matrix, which will convert the vector from view space to world space. Let's multiply it with our vertex. And since our matrix is 4 by 4, we need to convert our vertex to vec4 as well. And for W component, pass 1. Now it will also return back 4, but we simply need the XYZ components. And of course we want to normalize the entire thing, so that our ray direction vector will have the length of 1 unit. And now we have the actual sphere. But if we move our cube, our sphere stays at the origin of our world. The reason is our ray origin and ray direction are in world space. Now this could be useful if you want to create some sort of portal, but I want to move our sphere along with our mesh. So we need to convert ray origin and ray direction in local space or object space. To convert camera position to local space, we will take model matrix, which converts vector from local to world space. We want opposite of that, so we will do the inverse of that. Then we will multiply it with our camera position. Camera position world is vector 3, so we need to convert it to vector 4. Then we will take only x, y and z component of the entire thing. Now here we have converted vertex position in world space, and instead of adding one more operation, there is a better way to do this. In our vertex processor, we can get vertex position in local space, so let's just pass that position in our fragment processor. We can do that using varying. Let me declare a varying variable vec3vert. In our vertex processor, we will grab the vertex position in local space. Lastly, in our fragment processor, instead of all of this, simply use our vert variable. And now we can move around our mesh and our sphere will move along with it. Pretty cool! Now instead of red, let's assign our vertices xy components to see that it is actually a 3D sphere. So color.rg equals vert.xy. Now we can move the sphere by offsetting our point and get distance to surface function. So here let's say p minus some position. And we have moved the sphere a little bit. We can draw another sphere as well. Let's say this is sphere A. Let's define some different radius as well. Move our sphere B in opposite direction. Now to get the minimum distance, we will use min function. And we will return that. And we have two spheres. I can also make one sphere orbits around the second one. Let's put our sphere A at the center again. So for sphere B, let's put it away 0.4 units away from center in xz direction. We will multiply x component with sine of time and z component with cosine of time. And we have a sphere B orbiting around sphere A. Let me just reduce the radius of sphere A a bit. So you can see that raymarching is a very powerful tool for 3D shaders. We can do a lot with this, but this is just an introduction. I will give a more practical implementation in future video. You can also find the shader with various primitive shapes on my Patreon page, linked in the description below. Also, I know a lot of you watch my channel for visual shaders and shader graphs, and you might wondering how to implement this in visual shaders. Well, I am currently writing the nodes for raymarching in my add-on Shader-Lib, so soon we can replicate this via visual shaders as well. And that's pretty much the video. If you find the video helpful, hit the like button, share it with your friends, subscribe for more videos like this. If you have any questions, post them in the comments. Wishlist Cosmic Roads on Steam. That's it from me, and I will see you guys in the next one.